Up to this point, we focused primarily on what logic circuits do. Given a particular set of inputs, we determine the outputs by applying Boolean algebra, truth tables, or logic gates. But there's an important detail we've mostly ignored, and that is, when do things happen? In real digital systems, signals don't change all at the same time. You have input transitions, they go from 0 back to 1 again. And in fact, it's a voltage level. It may not be a perfectly clean transition, but we want to be able to discuss this and we want to be able to talk about it. It turns out in real life, gates require time to respond. Clocks coordinate operations across entire systems. And so as a result, we need some way of understanding a circuit's behavior more than just knowing time-shot values of the outputs of circuits. So this is where timing diagrams come in. And in this particular video, I'm going to show you an idealized timing diagram where we're not going to account for gate delays. We're just going to look at the behavior of the circuit as it evolves over time. All right, so I have the time axis down here. I have a simple AND gate followed by an OR gate with three variables, A, B, and C. And we can just step through transitions for the signals and look at what happens over time. Okay, so let's get started. I'm going to press the next button, and what's going to happen is it's going to simulate time marching along, and the first thing that happens is the input A goes from a 0 to a 1. Okay, so this showed up on the logic diagram. The value of A is now 1, B is a 0. So this product term is still 0. Nothing changed on the output because 1 ended with 0 is 0. 0 is what it was before. 0 ended with 0 is 0. Okay, so nothing happened yet in terms of the output. But this does show that the input changed on A. Okay, go to the next step. And in the next step, we show a transition where B now has made a change. C is still 0. Okay, but now something happened within our circuit. We have 1 ended with 1. That gives us a product term that now turns into a 1. All right, so the product term ORed with, C is still a 0, but the product term is a 1. ORed with 0 gives me a 1 on the output. And so now I can see this input change from B caused an output change. Now, this is an idealized diagram, so I didn't assume any delay time between when that would happen. In real circuits, there is some delay time that happens between when the B output transitions, the product term transitions, and then the OR term transitions. For now, we're going to do idealized diagrams like this one, but later on we can account for some time delay associated with gates and changes. All right, let's move on. Okay, so for the next step, let's say that A transitioned back down to 0. All right, so we show that with the timing diagram. B is still a 1, as shown here. C is still a 0. What happens then is the product term goes back down to 0. Since C is a 0, the product of 0 with 0 is a 0. And so our output goes back down. All right, so this graphically shows this evolving over time. So the next step here, let's make C go to a 1. So when C goes to a 1, it doesn't matter what the product term is. The product term is still a 0. And so the output is 1 ORed with the product term, and we get a 1 on the output there. So that shows that step. Okay, so in this next step, C remains a 0, and that dominates. So the product term turns back on because what happens in the next step is A returns to a 1. So the product term also became a 1, but the output was already a 1. So nothing changed in that case. All right, and there's one more step. So in the final step, C gets put down to a 0. A still stayed a 1, and B is a 1. So the product term is still a 1. And so the output from the OR gate would still be a 1. All right, so the actual details of what exactly happened is not the point. The point is I can figure out this step by step and have a timing diagram that captures the evolution of how this circuit performed for these input conditions over time. All right, so that's your first glimpse of a timing diagram. We're going to use timing diagrams quite a bit in this course, and we'll add more detail in, like maybe it has, multiple bits on a signal path, and so we'll have a different form of a diagram for that. Maybe you want to account for delay times through the gates. We can do that as well. All right, so your first introduction to timing diagrams.